Somewhere in a laboratory, cooled to a temperature colder than the depths of outer space, a machine just did something that made headlines scream the words quantum supremacy. And almost immediately, a question started spreading across the internet faster than the scientists could explain what actually happened. Did a quantum computer just make ChatGPT obsolete? Is the AI you talk to every day about to be replaced by something so powerful it makes large language models look like calculators next to a supercomputer? The headlines are everywhere. The claims are dramatic. Some say the AI revolution is about to be leapfrogged entirely. Others say everything you have come to rely on ChatGPT for is about to be rendered primitive by comparison. And the real answer is more interesting, more nuanced, and frankly more important to understand than the panic those headlines are specifically engineered to produce, because understanding what actually happened tells you something true and useful about where technology is actually headed, instead of something false and alarming that simply generates clicks. This is the real story of what quantum computers actually are, what they just achieved, what they cannot do, and why the relationship between quantum computing and artificial intelligence is not a story of replacement at all. It is a story of something stranger and more powerful than obsolescence. It is a story of fusion. Let's start with what actually happened, because the underlying facts are genuinely extraordinary and do not need exaggeration to be impressive. In December 2024, Google released results for its newest quantum processor, a chip called Willow, containing 105 qubits arranged on a superconducting circuit cooled to a fraction of a degree above absolute zero, colder than most of empty space itself. Willow completed a specific benchmark computation known as random circuit sampling in under 5 minutes. The same computation, run on Frontier, one of the fastest classical supercomputers ever built, would take approximately 10 septillion years. That is a 10 followed by 24 zeros, a number so large it exceeds the current age of the universe by a margin that breaks human intuition entirely. This was not an exaggeration or a marketing claim. It was a peer-reviewed result published in the journal Nature, verified by independent researchers using established benchmarking methodologies, and it represents one of the most significant demonstrations of quantum computational advantage in the history of the field. Willow also achieved something arguably more important than the speed benchmark itself. It demonstrated for the first time that quantum error correction can scale in the right direction. As Google's researchers added more physical qubits to encode each logical qubit, the error rate dropped exponentially rather than climbing, crossing into what physicists call the below-threshold regime, a milestone the field had been chasing for nearly 3 decades since quantum error correction was first theorized. So the headlines are not wrong that something extraordinary happened. What they get wrong, badly wrong, in ways that matter, is what that extraordinary achievement actually means for technologies like ChatGPT, Claude, Gemini, and every other large language model the public interacts with every day. To understand why a quantum computer cannot simply replace an AI chatbot, you need to understand what these two technologies are actually built to do, because they are not competing versions of the same thing. They are fundamentally different tools designed to solve fundamentally different categories of problems. A large language model like ChatGPT works by processing language. It has been trained on enormous quantities of text, books, articles, code, conversations, and through that training, it has learned statistical patterns about how words and ideas relate to each other. When you ask it a question, it is performing an extraordinarily sophisticated kind of pattern completion, drawing on billions of parameters that encode relationships between concepts, generating a response one token at a time based on probabilities learned from its training. This is, at its core, a problem of pattern recognition and generation across massive but ultimately classical data. The hardware that runs these models, the graphics processing units, the tensor processing units, the enormous data centers full of specialized chips, are classical computers. They perform calculations using bits that are definitively 0 or definitively 1, executing matrix multiplications at staggering scale, but using the same fundamental logic that has powered computers since the 1940s. Just executed with extraordinary speed and parallelism. A quantum computer works on an entirely different principle. Instead of bits, it uses qubits, which can exist in superposition, holding the mathematical possibility of being 0 and 1 simultaneously until measured. When you link many qubits together through quantum entanglement, a phenomenon where the quantum state of one particle becomes correlated with the state of another, regardless of the distance between them, in a way that has no classical analog. The system as a whole inhabits a computational space that grows exponentially with each additional qubit. Add one more qubit to a quantum system, and you do not add one more unit of computing power, the way adding one more transistor does in a classical chip. You double the size of the space the system can represent. A system of just 300 entangled qubits can represent more possible states than there are atoms in the observable universe, a fact that sounds almost absurd until you understand the underlying exponential mathematics. This is an extraordinarily powerful property, but it is only useful for specific classes of problems where the answer can be extracted by exploiting quantum interference, where the structure of the problem allows quantum algorithms to find a solution exponentially faster than any classical approach. Problems like simulating the behavior of molecules at the quantum level, problems like factoring extremely large numbers, which underlies modern encryption, problems like certain types of optimization across enormous combinatorial spaces, problems where quantum mechanics provides a genuine computational shortcut. Generating fluent, coherent, contextually appropriate human language is not, as far as anyone in either field currently understands, a problem of that type. There is no known quantum algorithm that would allow a quantum computer to generate text the way a transformer-based language model does, and there is no theoretical reason to expect one exists. The tasks that make quantum computers extraordinarily powerful, sampling from extremely complex probability distributions defined by quantum circuits, simulating molecular interactions governed by quantum mechanics, solving certain mathematical problems that are exponentially hard for classical computers, are mathematically unrelated to the task of predicting which word should come next in a sentence based on patterns learned from billions of examples of human writing. This is the central misunderstanding behind every headline claiming a quantum computer has made ChatGPT obsolete, and it is worth naming precisely because the same misunderstanding will keep generating false claims about quantum computing for years to come unless people understand the underlying logic. The error treats computing power as a single generic resource, as if a faster computer is simply a faster computer, regardless of what kind of computation it performs well, the same way a faster car is simply a faster car regardless of the terrain. Computing does not work that way, and it never has, even in purely classical systems. But quantum advantage is task-specific in an almost absolute sense. Willow's stunning performance on the random circuit sampling benchmark tells you something important about quantum hardware engineering and about the boundary between what classical and quantum computers can efficiently calculate. It tells you essentially nothing about whether a quantum processor could write a coherent essay, hold a conversation, summarize a document, or do any of the things that make ChatGPT useful to hundreds of millions of people. These are not the same kind of problem any more than a race car being faster than a bulldozer means the race car can dig a foundation. There is a deeper, more technical reason why quantum computers are not poised to replace language models anytime soon, and it has to do with the current physical limitations of quantum hardware itself. Qubits are extraordinarily fragile. The quantum states that make them powerful are also what makes them unstable. Any interaction with their environment, any stray vibration, any tiny fluctuation in temperature or electromagnetic field can cause the delicate superposition to collapse, introducing errors into the computation. This is called decoherence, and it has been one of the central engineering challenges of quantum computing since the field began in the 1990s. Early quantum computers could maintain a coherent quantum state for only millionths of a second before errors overwhelmed any useful calculation. Decades of engineering work, better materials, better cooling systems, better isolation from electromagnetic noise, and increasingly sophisticated error correction codes have extended that window dramatically, but the fundamental challenge has never disappeared. Every qubit added to a system is both a source of additional computational power and a new potential point of failure, which is precisely why Willow's below-threshold result mattered so much to physicists, even though the public conversation focused almost entirely on the speed benchmark instead. Willow's breakthrough was specifically in error correction. Google's team demonstrated for the first time that as they added more physical qubits to form each logical qubit, the error rate decreased rather than increased, crossing what is called the below-threshold regime. This is a genuinely historic achievement in quantum engineering, but it is an achievement in making quantum computers more reliable at the specific tasks quantum computers are good at. It does nothing to give quantum hardware the capability to run the kind of massive parallel matrix multiplications that large language models depend on. In fact, running a large language model on quantum hardware would, with current technology and current theoretical understanding, be wildly impractical, even if someone wanted to try it. Training a model like GPT or Claude or Gemini involves processing trillions of parameters across enormous datasets, performing classical linear algebra operations at a scale that current quantum computers, with their hundreds of qubits, are nowhere close to handling. Quantum computers excel in domains where the problem size scales in qubits, not in the brute classical scale of trillions of numerical parameters that need to be multiplied and adjusted through gradient descent. The kind of memory and processing architecture that language models require is fundamentally classical in nature, and building a quantum analog of it is not simply a matter of waiting for more qubits. It would require an entirely different computational paradigm that does not currently exist, even as a serious theoretical proposal. So if quantum computers are not going to replace ChatGPT, what is actually happening at the intersection of these two technologies? This is where the real story becomes genuinely exciting, and it is a story almost nobody is telling clearly, because it does not fit neatly into a dramatic headline. The field is called quantum machine learning, and it represents a genuine, serious area of active research, where quantum computing and AI are being combined, not in competition, but in collaboration. Researchers are exploring whether quantum computers can accelerate specific subroutines used in training certain types of machine learning models, particularly models used in chemistry, material science, and certain optimization problems, where the underlying mathematics has a structure that quantum algorithms can exploit. Google, IBM, and a number of quantum computing startups, including IonQ, Rigetti, and PsiQuantum, have published research demonstrating quantum-enhanced approaches to specific narrow problems in machine learning. These include quantum kernel methods for classification tasks, quantum neural networks for certain pattern recognition problems, and quantum-assisted sampling techniques for generative models used in specialized scientific contexts. The research is genuinely promising in narrow domains. But none of it suggests quantum computers replacing the transformer architecture that powers modern language models, and the researchers publishing this work are, almost without exception, explicit about that limitation in their own papers. The honest scientific consensus, repeated consistently across the field, is that quantum machine learning is a complement to classical deep learning for specific structured problems, not a successor to it for general-purpose tasks like language generation. Instead, it points toward quantum computers, serving as specialized coprocessors for specific scientific and mathematical tasks that classical AI struggles with. Any of the most promising applications of this combination is in drug discovery and materials science, where AI is already producing extraordinary results, and quantum computing could push those results even further. Classical AI models like AlphaFold, developed by Google DeepMind, have already revolutionized the prediction of protein structures, solving a 50-year-old grand challenge in biology that had resisted traditional experimental and computational approaches since the 1970s, and producing predictions for more than 200 million proteins made freely available to researchers around the world. But predicting how molecules interact at the deepest quantum mechanical level, modeling electron behavior, chemical bonding, and reaction pathways with full quantum accuracy, is a problem that classical computers, even running the most sophisticated AI models, struggle to do with full precision because the underlying physics is itself quantum mechanical. This is exactly the kind of problem quantum computers are theoretically well suited to handle. Researchers are actively exploring hybrid systems where classical AI models handle pattern recognition and broad structural prediction, while quantum processors handle the parts of the calculation that involve simulating genuinely quantum mechanical interactions between atoms and electrons. Neither system replaces the other. Each handles the part of the problem it is naturally suited to handle, and the combination of the two produces results that neither could reach alone. A classical AI model can scan a database of millions of candidate molecules in seconds, identifying which ones have promising structural features. A quantum simulation can then verify with full quantum mechanical accuracy exactly how the most promising candidates would actually interact at the electron level with their target protein. A level of precision that classical approximation methods, no matter how sophisticated the AI behind them, currently cannot fully replicate for complex molecules. This same hybrid approach is showing promise in optimization problems relevant to logistics, financial modeling, and materials discovery, areas where classical AI can identify promising regions of an enormous solution space, and quantum algorithms can then search those narrowed regions with a speed that classical brute force search cannot match. Companies including IBM, Google, and a range of financial institutions have published early research into these hybrid quantum classical approaches, though it is worth being clear and honest about where this research currently stands. Almost none of these hybrid quantum AI systems have demonstrated a clear practical advantage over the best classical approaches running on current AI hardware. The field remains in an experimental, exploratory stage. Claims of quantum computers already outperforming classical AI on real-world business problems should be treated with significant skepticism, because the engineering challenges of building quantum computers with enough stable qubits to outperform classical systems on practical tasks, rather than narrow academic benchmarks, remain substantial and unsolved. This brings us to an important and often overlooked point. The same fragility that makes quantum computers unable to replace language models also limits their usefulness for nearly all practical, everyday computing tasks, at least for now. Willow's historic benchmark, the 10 septillion years result that generated so many breathless headlines, was achieved on a problem specifically chosen because it plays to quantum computing's strengths and has essentially no real-world practical application on its own. It was, in the most honest framing, a demonstration of capability, proof that quantum hardware can outperform classical hardware on a carefully selected task, rather than a demonstration of quantum computers solving a problem that matters to ordinary people or ordinary businesses. The path from this kind of benchmark to quantum computers performing useful, economically meaningful work that classical computers cannot already do is still measured in years, and by most expert estimates, in many years. None of this means quantum computing is not important, or that its eventual impact will not be enormous. The opposite is true. As quantum hardware matures, as error correction improves further, as qubit counts grow into the thousands, and eventually the millions needed for certain transformative applications, quantum computers are expected to revolutionize specific fields where their unique computational properties provide genuine advantages. Drug discovery, where simulating molecular interactions at full quantum accuracy could dramatically shorten the development timeline for new medicines. Materials science, where quantum simulation could identify superconductors, battery materials, and catalysts that classical computational chemistry cannot accurately model. Cryptography, where sufficiently powerful quantum computers running Shor's algorithm could eventually break the encryption schemes that protect the modern internet, which is precisely why governments and technology companies are racing to develop post-quantum cryptographic standards years in advance. Optimization problems in logistics, finance, and engineering, where the combinatorial complexity of finding optimal solutions among astronomical numbers of possibilities is exactly the kind of challenge quantum algorithms are theoretically built to address. Problems like routing thousands of delivery vehicles efficiently, optimizing financial portfolios across enormous numbers of variables, or designing efficient supply chains across global manufacturing networks, all of which involve searching through solution spaces too large for classical brute force methods to fully explore. But generating an essay about the French Revolution, debugging a piece of Python code, summarizing a legal document, or holding a natural-sounding conversation about your day, the tasks that define what large language models do, are not on that list, and there's no credible scientific roadmap suggesting they will be anytime soon. The architecture of modern AI, built on transformer networks running on classical hardware, is not a placeholder waiting to be replaced by quantum computing. It is a different and, for these specific tasks, fundamentally better suited tool. Just make ChatGPT obsolete. Is the AI you talk to every day about to be replaced by something so powerful it makes large language models look like calculators next to a supercomputer? The headlines are everywhere. The claims are dramatic. Some say the AI revolution is about to be leapfrogged entirely. Others say everything you have come to rely on ChatGPT for is about to be rendered primitive by comparison. And the real answer is more interesting, more nuanced, and frankly more important to understand than the panic those headlines are specifically engineered to produce, because understanding what actually happened tells you something true and useful about where technology is actually headed, instead of something false and alarming that simply generates clicks. This is the real story of what quantum computers actually are, what they just achieved, what they cannot do, and why the relationship between quantum computing and artificial intelligence is not a story of replacement at all. It is a story of something stranger and more powerful than obsolescence. It is a story of fusion. Let's start with what actually happened, because the underlying facts are genuinely extraordinary and do not need exaggeration to be impressive. In December 2024, Google released results for its newest quantum processor, a chip called Willow, containing 105 qubits arranged on a superconducting circuit cooled to a fraction of a degree above absolute zero, colder than most of empty space itself. Willow completed a specific benchmark computation known as random circuit sampling in under 5 minutes. The same computation, run on Frontier, one of the fastest classical supercomputers ever built, would take approximately 10 septillion years. That is a 10 followed by 24 zeros,